Thank you for the introduction. Yes, so with DIC techniques, these are DSC, digital image correlation techniques. So my name is John Fries from Eindhoven University of Technology. Okay, just because we only have 15 minutes, I rush a bit through the motivation. But so we did some previous work where we looked at delamination microelectronics together with Philips. For instance, you have this copper lead frame and the multi-component epoxy, and there are all these interface cracks going on. And to do this, this is previous work, right? So this, some years ago, we developed a miniature mixed mode bending setup to do at a very small scale to do delamination test in mode 1 all the way up to mixed mode. So we could choose this. You can see here, this is sort of the insert in our dental tester here. And this is a 1 euro stamp, so we made it actually quite small. And the reason we wanted to do that is that so we could take the whole device and put it in under an optical microscope or in an electron microscope. And if you do that, then you can do, for instance, make movies like this, where here we have a strain map of the ongoing crack, and this is the crack opening displacement profile during the delamination test. So we were interested in the mixed mode interface behavior of these interfaces. And to go from here to really traction separation laws, that actually worked, and we published some publications on this, how we can do this. But in the end, going from here to here wasn't so satisfactory, because we needed all kinds of tools that were like separate tools basically that we obtained from literature. And we needed to combine these, and in the end we got it working. But we were thinking this somehow there should be a more direct way to do this, and that motivates me for the present presentation, and it's integrated digital image correlation. So the idea is that you would have a test, and you would make a movie of it. So you have a series of images, and then you would have a model, like a kinematic description, for instance, of your DCB test. But in this case, this could be an analytical model, and actually we're also working in parallel on this. This could also be a finite element model. So what I'm going to be presenting today is such a finite element model of such a DCB test. And then you get a displacement field as a function of your material parameters, which in this case are material parameters describing the interface behavior. Then somehow, if you would have this model, you would be able to walk back all these images back onto the original image, if your description was correct. That means that if the model was correct, and if your parameters actually are the correct ones. So basically, this means that all of your information is in here. So you would also not have to use a force measurement. And ideally, this is just a double clamp beam test, and people have worked on that a lot. It's a nice model test. But ideally, just imagine this would be a computer chip with all kind of complex layers, and you would just make a finite element model of this. Then you would still be able to do this. So in a very complex geometry with many different materials and everything. So that's where we sort of like the goal in the far future maybe is going. But this is sort of like the idea. So integrated DSC, how does it work? We would have first an experiment here. So this is again the same miniature mixed mode bending setup under an optical profilometer with a pattern applied to this for digital image correlation. So we would have a series of deformed images, and we would compare these to the reference image. So each one would be compared. And so the basic equation that is being solved in digital image correlation is brightness conservation, which means that a brightness point the brightness in reference image at point X should be equal to the brightness at point X plus U in the deformed image G. And there U comes in, that's the displacement field, and the displacement field itself then depends on lambda, which are the parameters. These are the material parameters we're interested in. And this should be 0 in the case that everything works well, but normally there's noise, and then this would not be 0. And this would give you your residual. So what we would be doing here, in order to solve this equation, we literally take f minus g, but here we need to look at different places than here, because we need u. So what is u? Well, we take this from a finite element simulation. So the finite element simulation gives us the displacement at each point. So now we know which brightness here to compare with the brightness there. So we just do this subtraction, let's say given here, and then you get a residual field. And you get a residual for each of these images. Now we normally warp the model on top of each other and then extract just one number from it, and we would say whether or not this residual would be good or not good. And if it's not good, then these input parameters that went into the simulation will be adapted. So that's delta here. We would make an adaptation here, and then we compare again. And we would look over this until we would have convergence in the sense that the residual would be low enough to what we would like it to be. And then you can also always look if there are systematic regions where the displacement is high. For instance, in this example, this might be good enough, but here one of these images might be very bad, and this would give you an indication that your model is not good enough. So that's the idea. This morning I figured out that I have less time than I thought, so I might skip a bit very quickly over this. We did a study actually where we compared integrated DSC with finite element updating, which is a much more known technique. Finite element updating is basically a two-step approach. You first have image series, you get a displacement field with a local DSC method, and then you try to match this displacement field using finite element simulation. But in integrated DSC is a one-step approach. So you use the simulation to directly warp back the images on top of each other. And in that we can actually avoid some of the assumptions in there and some of the inaccuracies. We compare this, and this goes a bit too much in detail, but the main thing here is basically if there's more complexity or some more systematic errors like model errors, then IDEC is performing better than finite element updating. In many cases they would be the same, basically. It's not that it's much better, but it's integrated DSC. We couldn't find a case where it performs worse, actually. We published this in IGNME and a group of François Hilton had a sort of like similar publication in experimental mechanics, both last year. Okay, so let's look at this, and now we want to apply this to a real experiment. So this is an image series, and now we need to do a simulation. And now the question, of course, is what kind of boundary conditions should we apply there that actually match the experiment? So our first guess is that we do sort of like a local DSC here, and from that we extract the displacement points at these 4 points and these 4 points, and we apply it here, and that is how we do the simulation. And another thing is that we probably understand that this is not absolutely accurate, but that's fine because the region of interest that we're actually comparing, where the process zone is just here, so this is the region of interest that we're going to be correlating. And we did this, and to our surprise, actually there was no convergence. This is the initial residual in this region here, and after iteration it didn't converge at all. So we have a problem here. So we thought maybe this at the interface this is not good, so let's mask this out of the region here, and it still didn't converge. Then basically we left the mask in, but we need to go a bit further and looked into this. And then we looked into the sensitivity maps. Basically, this tells you if I change the material parameter, how sensitive it is to the residual. How much with one material, how much can I actually influence the residual? And it turns out that these elastic parameters, like the Poisson ratio mostly, they were really not sensitive. So in this case, it's already a bit of a pity, but okay, let's assume that it's still okay. And we just assume that we know we locked these elastic parameters, but still we didn't have any convergence. Okay, now we had a bit of a problem. Okay, so this whole theory sounded very well in theory, and in theory it worked better than finite element updating. In practice it was not working. So what could we do? We went back to, well, we went back to virtual experimentation. So we noticed actually that here already, oh no, okay, wait, before we did that, sorry, we noticed that already here, near these clamps here, that there was errors. So we're thinking this is not good enough. Maybe there's a glue layer here that's doing something funny, which we're not capturing. So the next thing we did, we had a local region here, and we extracted these 3 points on the virtual line, and then we applied that, and still no convergence. And yeah, and again, still there was some errors here. even here in this region. So we were thinking, okay, what's going on? Let's go to virtual experiments. So this is now a virtual experiment. It looks a bit funny because here there's also material here. That's just because there's a cohesive zone in the finite element simulation, and it's basically just a pixel that's being stretched. In reality, that wouldn't happen, but in the virtual experiment, that's no problem there. So we have an artificial pattern. We have known model parameters here now. And the first thing we tried is that in this, so we simulated these experimental images now, and in our integrated DSC algorithm to extract back out the same material parameters, we applied exactly the same boundary conditions as in the finite element test to create the images. If you do that, then it's successful. Good convergence, less than 1%, actually much less than 1% error in the parameters. This is working. So again, the technique is working. So, and we said, okay, this also works if you don't take such an artificial pattern, but you take the real pattern and you start forming it, no problem. It also works actually if we take inhomogeneous cohesive zones here in the simulation, we start fitting this. We can also extract it out. No problem there. This is so you can, even in inhomogeneous interface, in theory, you should be able to extract out inhomogeneous interface parameters. Okay, so why is was the experiment not successful? Well, the main difference is in boundary conditions. Right, so here we apply exactly the same boundary conditions as in the simulation to generate the images. So let's test this out more. So now we kept the virtual experiment the same, but we started changing with the boundary conditions. And the first thing we thought was, okay, let's have an area here, and we do DSC on this. And so we have basically, we have this simulation here, and we can do DSC on it to extract out the parameters. We do this for the whole region, so we know exactly how this moves. We put in exactly the right kinematics, and then we correlate again on this region to extract out the material parameters. And we apply, actually, we either do this on 2 regions or 3 regions, and we apply the displacement in X and Y direction, and it completely diverges. This doesn't work. So it is really sensitive to these boundary conditions. So what could we do? Okay, and the reason is that if you have boundary conditions that are, for instance, working in the same direction, and if you first have to determine them with DSC locally in this region, and just a small error gives you huge stresses locally, and they work inwards into your region. So the next thing is, okay, let's more resemble the virtual experiment just by one point here, and still divergence here. So one point is that now actually we realize, okay, now we're not exactly describing the same boundary conditions anymore, because normally you would, if you apply in the virtual test, you apply a displacement here, that would give a different moment than if you apply it here. So we said, okay, let's have 2 of them, so we apply basically an angle at these 3 points or 2 points. Well, okay, now we're getting closer, 50% error. Okay, if we have 3 of them, with 3 points, we can actually describe the curvature locally on these 3 points, or on only 2 points. Okay, now we're getting closer, 10% error. But now actually we realize that the curvature is linearly changing. So if you would have 4 points, and then we would sort of like impose already a bit that this curvature would sort of like linearly change, and this would work inwards in this region where we want to correlate. Now we're getting very close. 1%, less than 1% error. So now basically this was a whole study to figure out what kind of boundary conditions to apply. So let's do this now in the real experiment. So we do the same, we have this region from which we do sort of like a local DSC, we extract out these 4 points, and we apply this, so we apply the curvature, and which is linearly changing. Now it's converging. Now we go from the initial residual to this kind of residual. And what we also find that there's a fracture toughness. Well, this was just a test sample of 2 steel layers glued with an RL dyed glue. We have very good agreement with the GC from if you just do an area under a force displacement curve. So that's working nice. But this was all a bit of delay. I would have hoped to have been presenting a bit more. This is just quite recent. Now we really get a handle on it, but definitely we need more tests. So at this moment, the only thing I can say is that I still believe integrated DSC is a powerful tool, and it seems to be more accurate than finite element updated, especially for complex cases and where you need high sensitivity, like these interface parameters. And the image residual is very powerful. It tells you a lot on where it's going wrong. But we have a high sensitivity to model errors. That's good and that's bad. That means you need to get everything correct in your model and how you apply it. You really need to simulate exactly what you're doing in the experiment. And if you don't have that, then it just goes wrong. But if you have it, okay, then you know also that you really understand the experiment. But we still have a low sensitivity to interface parameters. If you change these interface parameters, it basically has a very small effect on the displacement field around the interface. And therefore, these boundary conditions application is very critical. But it seems like the interface parameter identification seems successful, but we need more tests. Just for the future, the next thing is then also to look at inhomogeneous interface parameters, which was already successful in the virtual test, but we would expect some problems again in the real test. But it should work, and also mixed mode loading. The way we apply on both sides, basically, it's completely set up also for mixed mode loading. So hopefully, thank you.
Thank you very much for the presentation. We have time for one quick question.